Now, in the previous video, we have learned that when a current carrying loop is placed perpendicular to a plane, and if we consider a small element on it, AB, then it produces a magnetic field which lies in the plane of the surface. If the loop is like this, if the loop is placed like this, then the magnetic field produced by it lies in the plane, and its demonstration is done here symbolically. This is the loop. We consider AB, small element dl. This is the radius vector, and for this the magnetic field produced here at P, which is at x distance away from the center of the loop, is dB, and this angle is theta, so this is theta. dB is resolved into two components, dB cos, dB sin. Now if we consider several elements like this element, or this element, or this element, or this element, or this element, every element produces their respective dB, like this one, this one, this one, like this is the point P, and the magnetic fields are like this, or this, or this, or this, or this. Every dB will be broken into two components. Now, for every diametrically opposite elements, the two cos theta components will cancel each other. That means no dB cos theta component will exist ultimately, and all dB sin theta components will join together to produce the net magnetic field at P. So to produce, now dB is by Biot-Savart mu naught upon 4 pi ideal sin alpha by r square. Now here the plane of the loop and the plane of the surface are mutually perpendicular, so alpha is 90 degree, that means 1 sin 91. To find out the total B, we have to integrate its sin theta component. This dB sin theta, all dB sin theta components are to be integrated. Now dB's value is put here, mu naught upon 4 pi I by r square. This sin theta, only dl will be under integration, and sin theta is a by r from this triangle, a by r perpendicular by hypotenuse, and dl, if you join all dl's, you will get the total circumference, that is 2 pi a. So the net expression will be this, and r, what is r? R is by Pythagoras under root a square plus x square, that means a square plus x square whole to the under root a square plus x square, that means a square plus x square to the power half, and it is r cube, so a square plus x square to the power 3 by 2. Now there is an option, and the option is, if this, we have to determine the magnetic field at the center of the coil or loop, then x is equal to 0, so at the center x is equal to 0, so B is equal to, if x is equal to 0, then these two and these two will cancel out, a cube with a square, so the final result mu naught upon 4 pi 2 pi I by a. If number of loops are there for n loops, n turns you must remember that I have mentioned about armature. In armature there are many turns, and if there are n turns, then this expression will be mu naught upon 4 pi 2 pi n I a square upon a square plus x square to the power 3 by 2. Okay. The next topic is Ampere's circuital law. Ampere's suppose there is a wire through which a current flows. Definitely, immediately it produces a magnetic field everywhere at every point around it, and all those points lie in a plane which is perpendicular to that current carrying conductor. Okay, if this is the current carrying conductor, and this plane if is perpendicular to this conductor, then when current flows through this conductor, immediately it produces magnetic fields which lie on the plane of this surface, on the plane of the surface. If we draw it in some kind of in a better way, like this, so if you choose several points, so due to this current, the magnetic fields like this one or this one or this one, all these magnetic fields are tangential to this line, and this is a closed path. And this small section of this path, suppose this is dl. If you join all these dl's, you will get the total path. So according to Ampere, the statement is the line integral of all magnetic fields along a closed path around a conductor is mu naught times the current flows through it. That means this conductor carries a certain amount of current, and all the magnetic fields produced around it, if are joined together, it produces a closed path, and this one, the closed path. So all the summation of all those magnetic fields will be mu naught times the current, this current. Symbolically, how can we express this? B this is vector, this is also a vector, small elements or small section of the closed loop. So we have to integrate, we have to make the sum of all those magnetic fields with respect to the small sections of the line. That means if we apply this symbol, this means closed path, integration of closed path. This is also called line integral, closed line integral. This is a closed line integral. That means যে ফ্যাক্টরকে আমরা ইন্টিগ্রেট করছি সেটা একটা ক্লোজড লাইন along a closed line act করছে. All the values of those magnetic fields around the closed path, which is framed by summing all those dl, is equal to mu naught times the current. Clear? Okay. Now this is the dot product, so obviously its value should be b dl cos theta, and for every dl and its corresponding b, what is the angle between these two? Suppose this is the total path, and if you consider this this dl, and the b acts like this, so what is the direction between dl and b? It is 0. So cos 0, that means from here we get b dl, line integral of b dl, this is 1, is equal to mu naught times I. Now if you join all the dl components, all the dl segments, you will get the circumference of the path of the closed path. If the radius is r, that means b into 2 pi r is equal to mu naught times I. From here we get b is equal to mu naught upon 2 pi I by r. If you change this factor as 4 pi, because it is more convenient for the application of the value of 10 to the power minus 7, so you have to multiply I with 2. Okay. Now how we can apply this method to determine the magnetic field at any point inside a current carrying solenoid. B, the value of B at any point on the axis of current carrying solenoid. It looks like spring, this one. So it carries current. Now if we apply the right hand palm rule, this one. Do you remember the right hand palm rule? It says that if you consider a current carrying conductor and if you grab the conductor in such a manner that the thumb shows the direction of current and then the other four fingers which are kept together will show the direction of the current carrying of the magnetic field produced. Now if we consider the solenoid like this one, this one in this pattern, and if the current flows this way and that way, then what will be the direction of the magnetic field? If this is the current, this is the current. If this is the current, suppose আমি কিছুটা better way তে draw করার চেষ্টা করছি. All the dotted lines are the turn behind and all the continuous lines are the turns in front. So if a current flows this way and it moves up that way behind, then again it comes in front this way and it comes and it goes behind that way. Okay. So if you place the thumb this manner, here is the current carrying conductor, this one or this one. So the magnetic field will move either this way or that way. That means the magnetic field, the magnetic flux, the direction of all the magnetic flux will be like this, parallel to the axis of the solenoid. If you reverse the direction of the current, okay, keep it in contact as usual. Then the current, if the current is like this, then the direction of the magnetic field this way. But if you reverse, then the magnetic field that way. This is the direction of the magnetic field. Now let me draw this in a miniature form. So these are the magnetic flux we have mentioned. Okay, all these are magnetic flux. B, the direction of B. Now let's consider a small closed path. A, B, C and D. Now the current, if this is the magnetic field, if this is the conductor, then the magnetic field will move vertically inwards. That means if the current is in the plane, then the magnetic field is perpendicular to the plane. And if the current is perpendicular to the plane, then the magnetic field lies in the plane. That means here the magnetic field lies in the plane. That means the current must go perpendicular to the plane. Vertically outwards, vertically inwards. This is the direction of current. In Ampere circuital law, we have seen that this all the direction of magnetic fields produced by this current, and this is dl. Suppose this is small element of the closed path dl, this is another dl, and the magnetic field is like this. This is B and this is dl. So in this case, this is B, this is the direction of B, this is the direction of current. So if we consider a small section of loop path, so if we consider this AD arm out of ABCD rectangular loop, if we consider this arm AD and BC, this is a DL, this is another DL, this is another DL, the segment of the path. Now the segment DL and the direction of B, this flux, the direction of flux and the direction of DL are mutually perpendicular in the case of these two arms AD and BC. But the direction of but the DC, if you consider DC and AB arms, then the direction of DL on these two arms and the direction of B are collinear. So if we apply the Ampere circuital law for this whole loop, according to him, the closed integration BDL is equal to summation of all the four segments. That means BDL for this part AB plus BDL for BC. That means এই A থেকে B এর মধ্যে যতগুলো এরকম DL আছে সবকটা DL কে আমরা সাম করছি, প্লাস C to D BDL plus D to A BDL. If you add these four, you will get the total closed path. The path is closed now. When you move from A to B to C to D to A, the path is closed. That means you have to add four segments together. Now we know that the direction of this is the dot product. That means its result is BDL cos theta. Now in the case of AD, this one, AD, and for BC. So in the case of this one and BC, this one. For these two, the direction of DL and direction of B are mutually perpendicular. That means cos 90, that is 0. So this will turn to 0. These two will turn to 0. And for CD, this segment is far away from the solenoid. This is the solenoid. We virtually draw. This is the solenoid. From the axis of the solenoid, this segment DC or CD is far away. So here the magnetic effect for this magnetic field is almost negligible. So we can neglect this part also. This part C to D. This part also. We can neglect. These two turns to 0, and this can be neglected due to its too low value, too small value. So remaining A to B BDL. If you assume that this length of AB part, AB segment as x, so when you integrate this DL part, you will get this length of x, that means it will be B into x. Now here, suppose this is the part AB. This is the part AB, and the terms are present in this manner. Suppose we have taken such a solenoid in which there are n turns, number of turns in unit length is equal to n. We assume that it is a kind of solenoid, but there are so different types of solenoids. It may be very dense, or it may be like this, where each turn is much further from the previous turn and next turn. So this is a solenoid where there are n number of turns in unit length, and each turn carries a current of suppose I. So according to Ampere, BDL is equal to mu naught times I. So if we consider here the current is I prime, how can you find this I prime? This BDL is equal to Bx. Bx is equal to mu naught times what is the current for this section? Each section carries a current of I, and each turn carries a current of I, and there are total nx turn, n into x, because unit length has n turns, x length has nx turns. Each turn carries current I, that means the total current I prime is equal to nxi. While you cancelling out xx, then B is equal to mu naught Ni. This is the magnetic field produced at any point on the axis of a current carrying solenoid.